So this is some joint work between myself, Adrian, and my advisors, Matthias Payer, excuse me, of EPFL, and Tony Hosking of ANU. So today we've heard a bunch of really great talks on all sorts of different aspects of fuzzing. And if we dig down into the different papers that people have presented on over today, we can see a common theme, that's not just fuzzing, but a common theme with respect to coverage. And that is, when we're talking about coverage, when we're talking about coverage-guided fuzzing, we talk about how AFL is greatly improved over, say, black box fuzzing because it has this coverage feedback loop in it. And what's so in a talk two talks ago, we heard about how different program configurations can, impact on code coverage. And we hear a lot about code coverage. And I guess what's kind of implicit when we talk about fuzzers and their coverage feedback mechanisms is that when we're talking about coverage, we typically mean, as Marcel pointed out in his introduction, control flow coverage. So that is taking our target program, decomposing it into a control flow graph, and then reasoning about and recording when a given input, hits either a vertex or an edge in that control flow graph. And, for the past, I don't know, a decade or so of fuzzing research and fuzzing work, both in the security community and I guess in the software engineering testing community, coverage typically means control flow coverage. But this is kind of starting to change. So last year we had some work presented at Usenix on using likely invariants as feedback for fuzzers. And I think this year pretty sure it's Euro S&P, there's another piece of cool work on looking at fuzzing with data dependency information. And what I really like about this stuff is that it's going, beyond the typical control flow based coverage mechanisms that we all are kind of used to in AFL and co, in that it's starting to look, less at the structural information and more at the actual data that programs are manipulating. So in this top paper, this work takes the LLVM data dependency graph and then kind of smooshes that in with edge coverage into AFL++'s coverage map. And similarly with this second piece of work on likely invariants, particular program variables in the program are instrumented to, again, capture that data flow information and the data that these variables are working with and, where they push the bounds of these invariants that have been learned prior to fuzzing. And so, I don't want to extrapolate too much here from just these two papers over the last 2 years, but there are other works as well, I guess. But what we're kind of seeing is that, the community is starting to look at alternatives to control flow coverage, this structural coverage, and we're seeing a little bit of a shift towards, data flow coverage becoming a quote unquote first-class citizen. So when I think about coverage and different ways that a fuzzer can incorporate coverage into its feedback, I like to think of it as kind of this spectrum graph thing. So note the caveat not to scale here. So on the x-axis, we have control flow, and then on the y-axis, we have data flow. And then, obviously we can have stuff in between. So if we just focus on the x-axis, as we go from left to right, we go from least sensitive coverage feedbacks to more sensitive. So that is, the higher the sensitivity, the more the fuzzer is able to discriminate between different states in the target program state space. But there's a trade-off here, right? Because as this sensitivity starts to ramp up, the fuzzer coverage map starts to saturate, the queue, starts to explode in size. And so there's a bit of a balancing act here. And the same happens as we go from bottom to top on the y-axis. So on the x-axis, if we think about classical AFL style edge coverage, we have two random identifiers, we XOR them together, and we use that to identify an edge in the control flow graph. And this is kind of less sensitive compared to some of the newer stuff that's going into AFL++. Because you can get collisions when that happens. So two, distinct edges in the control flow graph can map to the same entity in the fuzzers feedback coverage map. And so, so now we've got things like link time optimization. A couple of years ago, there was COL-AFL that kind of has this more intelligent hashing mechanism, sits somewhere in the middle here of this blue circle. And we can ramp up the sensitivity and we can start including things like function context sensitivity. So that is, the edge that's currently getting covered, what function calls have happened to reach that edge, all the way up to kind of path coverage. And a similar thing happens on the y-axis, right? So we can instrument, every single program variable in our target and look at all the data flows that are happening there. But this is probably not viable, right? So maybe we want to just, select a subset of these program variables. And then in the middle here in the orange, I've kind of got memory access here. And the reason I've got that in the middle is, again, I like to think of it as, depending on which way you cut memory access, I think of it as either a control flow metric or a data flow metric. So if you're only looking at a memory read or write happening, that's more of a control flow feature. But if you're looking at the values themselves that are being read or written, then that's kind of leaning more towards the data flow side of things. And so, like I've said, over the past decade, a lot of the focus has been on this x-axis. And what we want to do in our work here, and other work is also starting to do, is dive more into this y-axis. So that is the data flow. So for the remainder of this talk, we'll define what we mean by data flow coverage, and then we'll dive a little into how do we efficiently track this notion of data flow coverage in a fuzzer. So as we're all probably aware, iteration rate is king with fuzzing, right? If you slow down that iteration rate, the number of inputs or test cases that the fuzzer is able to generate, then this has a hugely adverse impact on your fuzzing outcomes. And so what we want to do is we want to strike the right balance here between, and the same happens in control flow coverage, in being as sensitive as we can to changes in the state space without too heavily impacting this iteration rate. And then finally, how do we plan to evaluate our techniques and ideas that we have here? All right, so let's define what we mean by data flow coverage. And so to do that, we're going to travel back to the future. Well, for me, that's before I was born. Maybe that's not the case for some of you, but we'll go back to September 1982. In ICSE, there was this work here on data flow analysis techniques for test data selection. So again, I think, calling back to Andreas's earlier keynote, this is, where we can, I think of myself more as a security person, we can look at, what the software testing engineering community has done. And there's a really rich body of work there that I think we can learn a lot from. And so in this work on, data flow analysis techniques for selecting test cases for test suites and things like that, we see some ideas that are similar to what I've already been discussing about on earlier slides, but from the software testing perspective rather than a fuzzing perspective. So for example, here we can see in figure 2, this hierarchy of control and data flow measures. This is, kind of what inspired me to do my coverage spectrum graph. And again, it tells you the same kind of story. So at the lowest level, we've got basic block coverage being the least sensitive. And then as we move up in our hierarchy, we get decisions or, conditional branches, which is edge coverage really. And then at the top, we've got, paths and also this DU path concept. And so for those that aren't familiar with this kind of work from software testing, this is def use chain paths. And so what is a def use chain? So a def use chain is a combination of a variable def site or definition site and where it is used. So if we look at figure 1 here, again from this paper, we can see the definition of variable I here when it gets assigned the value 1. And then we can see all the uses of I here in this sum, in this product, and the same thing with variable K and so on. And so we can construct this def use graph essentially by, having a vertex for a def, having a vertex for use and then linking them up, and then use that as a notion of data flow coverage. And so that's essentially what we've done here. So for us, we define data flow coverage as the tracking of these def use paths that the fuzzer executes at runtime. And so again, a def site for us is a variable allocation site, and this can be a variable that's statically allocated or dynamically allocated, so via malloc, calloc, and the like. And then a use site is where and how does that variable get accessed. So, reads, writes, or a combination of the two. And then, finally, our def use chain is this path between these two entities in our data flow graph. Okay, so in theory, this all sounds pretty nice and something that we can easily implement and stick into a fuzzer for its coverage feedback. But we run into a problem again of not killing our fuzzer's iteration rate. And so the problem is, and as this older work from the 80s kind of also points out, is that tracking all data flows is simply infeasible. And so what is our solution? Our solution, instead of tracking all data flows, is that we provide a mechanism for tracking different data flows at varying sensitivities. So again, this relates to the sensitivity work that has previously been done on control flow metrics, but now we can apply it to our ideas around data flow metrics. And so a couple of years ago in 2019, there was some work presented at RAID conference, security venue, on Be Sensitive and Be Collaborative, analyzing the impacts of coverage metrics in greybox fuzzing. And in this work, they kind of introduced this idea of having a sensitivity lattice to kind of theoretically reason about different sensitivities of control flow-based metrics. And so here we adopt the same kind of idea, but apply it to both def sites and to use sites. And so by composing these two lattices together, we can realize a different range, a whole suite of data flow def use chain-based coverage mechanisms, depending on how sensitive we want to be and what kind of performance hit, I guess, we're willing to take. So as with everything in systems, there's always a trade-off here. And so for def sites, for example, we partition by type. So if we instrument and track every variable def in our program, that's here at the bottom of the lattice. That's the most sensitive approach. And that's as if we did all types in the program. But say, for example, we're only interested in memory violation bugs, then perhaps we'll focus only on arrays. Or if we're interested in type confusion bugs, maybe we'll focus on structs and classes and that kind of thing. A similar kind of approach can be applied to use sites. So the most sensitive way of measuring instrumenting a use site is by looking at both reads and writes, which we just call access here, and also the data. So that is the value itself that was read and written in that use. And then the least sensitive way we can measure this is just by recording that a read or a write happened. And so that the least sensitive metrics again appear at the top of the lattice, and the more sensitive ones are down at the bottom. And in between, in this red zone here, we've kind of got this, what we think is kind of the halfway spot between these techniques, in that we're not really looking at the values themselves in the def use chain, but at more fine-grained spatial information. So if we're reading or writing into some object, whereabouts into that object are we accessing? And like I say, we can compose these things together to do the desired sensitivity. So again, how do we do this efficiently? So this is our overall system diagram. More detail is kind of in the paper. And today I'll kind of only focus on the runtime component. So how do we track these def use chains at runtime? And the way that we do this is reducing our data flow tracking to a metadata management problem. So now we've got our identifiers for def sites, metadata, and that we retrieve this at our use site. And then we can combine this information as our def use path or chain, and then stick this into our coverage map for the fuzzer. And the way that we do this is via mid-fat pointers and a custom memory allocator. So here's an example program. We've got a couple of def sites here. We've got variable A, variable B defined, and we've got a use of variable here. What we do at instrumentation in LLVM is we replace these def sites with our own custom allocation routines that also incorporate an identifier for those def sites. So here we've got identifier 1, 2, 3, 4, A, B, C, D, and then we can record memory accesses, again, with similar instrumentation. And then this maps across into our memory allocator that kind of uses this mid-fat pointer idea to keep track to allocate memory according to these def site identifiers. And so that means we can efficiently access the def site ID just by a shifting operation. So at our use site, we can grab the def site, we can mark the use site just by using the current value of the program counter, and we can combine all this information together to get a unique index into our coverage map. All right, so that's kind of the idea that we've hypothesized for tracking def use paths and hence data flow coverage in a program. So how are we going to achieve this? So some of the questions that we're particularly interested in answering is how can we characterize a type of program for whether it will, is amenable to this data flow coverage idea, or whether data flow coverage is simply subsumed by control flow coverage. So a lot of the times, data flow is maps pretty closely to control flow. So we probably don't need to use special data flow tracking techniques. But for other kind of programs, say like LR parsers, table-driven parsers, where you have this tight loop, then in that tight loop, you're executing the same control flow over and over again, but the data that you're operating on changes. So, if we can characterize those programs, then we can figure out, where this kind of technique is useful. And then the second research question is on quantifying data flow coverage. So if you look at Fuzzbench, the standard technique is, you take the coverage map, snapshots of the fuzzer queue, and you replay those seeds through a source code Clang instrumented version of the program, and you get line coverage. But does that really make sense if we're not focusing on control flow coverage anymore? So how do we then, because again, if we're thinking of that LR table-driven parser, the line coverage is going to look the same, even though we may be exploring different parts of the data flow. And so, how do we think about this, beyond just the standard normalize or convert everything to line coverage? And then finally, is this type of fuzzing, is it effective? Does it bring us new ideas around coverage and code exploration or target exploration, and also, bug finding techniques. So that's about all I have for today. So there's a lot more detail in our registered report, and our code will go up after this talk, and I'm happy to field any questions.